Modern machine learning models hit a hard compute limit as data scales up. They cannot look at everything simultaneously. To function efficiently, an attention mechanism must learn to identify which sparse pathways matter, severing the vast majority of connections to save processing power. This restriction is formalized as a sparse attention edge budget. The model is granted a strict allowance, exactly k active connections per query node, and it must choose how to spend them. To evaluate how well a model makes these choices, researchers test them on a synthetic hierarchy. This is a controlled, tree-structured dataset. From a central query node, we can test exactly which surrounding data points the model chooses to read. A basic distance local proximity mask spends its budget on the nearest physical neighbors, the siblings. A perfect oracle mask, built using the ground truth structure of the data, allocates its budget to reach both those local siblings and a structurally distinct parent node. The performance difference between that simple proximity routing and the perfect structural routing is the oracle gap. Closing that gap serves as the primary metric for proving a model's architectural capability. This raises a specific question. Can a learned, content-based sparse router analyze data to close the oracle gap and discover that structurally distant parent node? The standard assumption in evaluation design suggests that constructing a task where the target node sits outside the nearest neighbor radius forces a model to learn content. Testing this assumption requires two adversarial campaigns against the data generator. The first campaign is an instrument hardening ladder, a sequence of repairs to seal data leaks before evaluation begins. The second is an attribution reversal that interrogates the winning model's behavior. Accepting architectural success without environmental audits risks the publication of sophisticated illusions. Initial generator tests show the environment fails to isolate the routing question. Multiple side channels allow the model to find answers without performing genuine routing work. The first failure is subtree payload correlation. The parent node's specific payload pattern carries down to its children. A proximity router reading only local children is granted the distant parent's answer, successfully predicting the parent without actually routing to it. Removing that correlation reveals a second failure, transductive family leakage. Because sibling nodes appear during training carrying a family constant parent label, the model memorizes the mapping. During evaluation, a node's features reveal its family, allowing the model to retrieve the answer from memory instead of routing to find it. The structural fix involves strictly held-out payload worlds. Resampling the payloads for every world makes the label independent of any stable geometry. Without these preemptive, strict falsification gates, structural data leaks will consistently masquerade as architectural learning. Even with the data isolated, the testbed presents a subtle leak in the evaluation baseline itself. The absolute floor of performance, the no-information Bayes ceiling, is mathematically definable by simply guessing the most common class. This diagnostic scatterplot compares local head accuracy from a no-routing probe against the empirical baseline. Notice the points falling below the diagonal tolerance line. The random sparse network underfits the mathematical prior, and that shortfall grows as the edge budget increases. Because the baseline sits artificially low, it triggers phantom leakage flags, rendering valid models as failures. The necessary correction replaces the learned empirical baseline with the strict analytic marginal mode frequency. Relying on rigid analytic mathematical nulls prevents measurement biases from destroying valid experiments. The testbed is now certified. The parent node is strictly isolated outside the nearest neighbor reach, with no statistical side channels remaining. We can now test the learned content router, forcing it to use node content to score and select its sparse connections. This bar chart measures the weighted test accuracy across the baselines and the learned variance. The data presents an initial victory. The learned sparse variant posts a statistically significant accuracy lift, clearly outperforming the fixed distance local baseline. This chart deconstructs the score. The orange bar shows the learned sparse router successfully lifting parent accuracy, apparently finding distant data. But the blue bar reveals the cost. To grab the parent, it surrendered its local accuracy entirely, collapsing to the mathematical prior. The oracle mask proves that the budget is large enough to cover both targets simultaneously. The learned model failed this joint coverage requirement. It simply traded local edges for a distant one. A superficial win on a top-level weighted metric can easily mask a complete allocation failure. We must now ask a decisive attribution question. Did the model actually use its content reading capabilities to find the distant parent node? Answering this requires a capacity-matched control as a mandatory attribution instrument. We construct a distance-only capacity router. It shares the exact architecture as the original, but the data payload inputs are stripped away. This control variant is completely blind to data payloads. It receives only pairwise embedding distances as its input. This sets up a strict trap. If the original router succeeded because it learned to read content, this blind control network must fail to find the parent node. Attributing a model's success to a specific feature requires proving the model fails when explicitly deprived of that feature. The blind control network does not fail. This chart isolates parent-head accuracy attribution among the routers. The distance-only capacity router recovers the unreachable parent perfectly in every seed. It closes nearly twice the gap of the content router and outright beats it on performance. The explanation relies on a strict geometric rule. Rank-based unreachability is not distance anonymity. The standard assumption in machine learning is that pushing a target outside the nearest neighbor radius hides it from geometric algorithms. But forcing a node precisely outside that radius doesn't make it anonymous. It stamps the target with a highly identifiable, unique distance band signature. The neural network ignored the semantic content entirely. It simply learned a non-monotone rule to reach past the immediate neighbors and grab that specific geometric ring. Even with this geometric trick, the models still failed to cover the local and distant nodes simultaneously. The unclosed residual of the oracle gap is a limitation in how these models allocate their budget. The learned model bypassed the problem, exploiting geometry rather than fulfilling its promise of semantic content routing. This study provides a reusable, ruthless falsification protocol, strict gates, analytic nulls, and capacity controls to prevent believable geometric illusions from masquerading as architectural breakthroughs.